continue. So we ended with this one, quantum of action. And what is this Planck constant, which is quantum of action according to Niels Bohr? So Planck constant, how did it appear? It appeared from completely other task or say problem or puzzle. There was the like radiation of the black body radiation. Okay, so this is also was revolutionary because Planck proposed a formula for black body radiation in exactly the year uh, 1900. Okay, so you see, this black body radiation, well, it's nobody could understand why this maximum is achieved and on what it depends. And so there were different solutions proposed. So the right way which Max Planck, a German physicist, have chosen was that there are so-called quanta of radiation quanta. So this also one of the possible explanations of how quantum theory started. So before it was supposed that radiation is like continuous. So you can radiation is not how to say, doesn't consist of certain quanta of light. So radiation is continuous. It's only has wave nature. No, because quanta introduced kind of a corpuscular, okay, corpuscular idea, corpuscular. You know, corpuscular. I don't know how to you pronounce this word, corpuscular. Anshita, I'm pronouncing correctly or not?
Corpuscular.
Corpuscular, yes. So
Corpuscular.
corpusculum is a little body. Corpus is in Latin body. Corpuscular is small body. Okay. So corpuscle. You can say also in English corpuscle. Yes. Corpuscle. Yes. It's like a in little very small body, like atom, for example. So small particle. Oh, just particle. Small particle. Okay. Small particle. So, well, Newton was also thought of light as a flow of small particles. Small particle. But Newton's idea was disproved by wave theory of light because Newton couldn't explain such phenomena as diffraction and interference. And this, optics, diffraction of light, diffraction or interference, this of light. So these both phenomena could be understood only in frames of the wave theory of light, okay? So by the end of the 19th century, wave theory gained the upper hand, okay? Angel Sierra, am I correctly speaking? So everybody believed, Maxwell and Hertz and other prominent physicists believed in the wave theory of light. Corpuscular theory was thought outdated, uh, in spite of the fact that Newton was the champion of corpuscular theory of light. Nevertheless, Newton was sort of considered like erroneous. A Newtonian idea of this corpuscular theory of light was considered erroneous, and everybody believed in the wave theory of light. But when they tried to explain the black body radiation with the classical wave theory of light, they came to a paradox, or so-called ultraviolet catastrophe. You can just Google it, ultraviolet catastrophe. Well, if you Google this, you will find interesting information. Catastrophe. Yes. Well, somebody try ultraviolet catastrophe. If you haven't if you haven't heard this like expression before, just take how to say, just try to understand what it is. Maybe Angel Sierra knows what is the ultraviolet catastrophe.
Yes.
Explain to us what is this expression? What does this expression means? Ultraviolet catastrophe. How it is connected with black body radiation?
First, with the black body radiation, a black body is a body who absorbs all kind of radiation,
Yes.
and because of this,
Emitted through the small hole. Okay. So
yeah,
the radiation is like in we say in Russian равновесие, but in I will see it's равновесие. I, balance, yes, it is in balance with the it is in balance with the and how to say, with the energy of the body. So somehow this radiation and atoms in the or temperature in the body are in like in balance. Yes. So well, ideally this radiation is emitted through a small hole in this black body. Okay. But of course we can regard, for example, in some approximation, even our sun as the black body. Okay. So this formula for black body radiation also can be applied to our sun radiation, because of this equilibrium or balance between energy of matter and energy of radiation. Okay. Well, it's just I try to explain difficult things in well, very briefly, but well, you can just see the articles in some encyclopedias on Wikipedia. Even I think English Wikipedia in physics is more or less correct. So you can see these articles: black body radiation, ultraviolet catastrophe, and Planck formula. Okay. So classical approach of wave theory was not enough to explain the experimentally received results about black body radiation. Even the light of the sun and why sun is yellow, okay, couldn't be explained. Okay. So this maximum, we see sun is yellow. So well, and this according to Planck's formula, this color of the radiation or wavelength of or where the radiation is receives maximum, or this is only dependent on temperature. So for every temperature there is a certain say wavelength. Well, it can be seen if you, for example, start to heat the metal brick, okay, brick made of metal, for example, or iron brick. If you start to heat it, at first it will be red, and then it will become like violet, or we can say white, okay. So this the wavelength will sort of the light will uh, decrease, okay. So and the frequency will increase. So what did Max Planck suggest? That this radiation is emitted not continuously in like waves, but in some particles with energy h um, h nu. Well, I don't have nu, so I will just like write v, okay? But you recognize it. So h nu is equal to energy, okay? Do you know this formula? Angels, yeah. Follow the chat.
Yes, yes, I
Sounds familiar, yes? Okay? Looks familiar, yes? This formula. Anshita, you have lost the thread of my lecture or not?
No.
Have you seen this formula? H nu is equal to energy.
I have seen H nu at MIPT's login.
What is that? Ah,
MIPT
it's yeah. Okay, it's a law of
building.
MIPT. Yes. So this formula can be found even on the fence. If you
Yeah.
approach MIPT by Институтский переулок, you will see the fence, and on this fence you will see this formula H nu, okay, or energies. Well, this, why is it so popular? Because it is like the motto or like the sign of scientific revolution, which happened, which is our theme, scientific revolution of the beginning of the 20th century. So this revolution consists of changing from classical mechanics to quantum mechanics. And also we introduce again the corpuscular theory of light. So now light is not only wave, but
Professor, I I shared a file. In this image is the comparison with the classical curve and the observed spectrum of the black body.
yes,
So the term of the ultraviolet catastrophe is the difference between the classical path, that the prediction,
yes,
classical theory, with the small
with a
wavelength.
quantum theory. Okay,
Yeah.
so classical theory, we can say it this way. Classical theory leads to ultraviolet catastrophe. If we apply classical theory to the explanation of black body radiation, it will lead to ultraviolet catastrophe. We will not find the formula. So formula which Max Planck found for black body radiation can only be achieved if we suppose that radiation is not only a wave, but a particle, a kind of a particle. Particle which carries energy dependent on its frequency, nu. It is nu, not V. You see, this is a Greek letter nu, okay, which is stands for frequency, yes, of light. So now, if we see the dimension of this h, which is Planck's constant, we'll see that it has the dimension of action. So we return now to quantum of action. And now Niels Bohr suggests his explanation why atoms do not emit radiation, why atoms are stable. So how he solves this problem of instability of atoms. Because you remember we said that if electrons move around the orbit or orbit the nucleus, so the orbital motion is rotational motion. Rotational motion in classical mechanics is accelerated motion. Accelerated motion leads in the of the particle, charged particle in the electric field leads to radiation. So why atom is stable, why doesn't it emit radiation? So now we can solve this, how to say, paradox by means of quantum of action. So there are certain orbits of electrons which on which electron does not emit light. It emits light only when it comes from one orbit to another, and there is a finite set of such orbits. So and these orbits are proportional to we can find energy which say electron loses when he comes from one orbit to another or emits some quantum of light, and we see that this quantum of light depends on the sort of like dimensions or radius of this orbit. So this can be easily calculated, and but the principle which underlies these Niels Bohr calculations or postulates is that the action is changed only in integer numbers multiplied by h, which is Planck's constant. So here we see that motion is not continuous, that so we can say that electron sort of moves in leaps, and we cannot say that there is a trajectory of electron. We cannot say that electron is moving on a certain trajectory. We can say that electron exists in some state which can be stable, and if the state is stable, then the atom does not emit light. Well, if but there are a finite set of these states. So if electron moves from one state to another, then it can emit light or radiation, quantum of light. And so by this hypothesis, Niels Bohr not only explained well, sort of escaped this contradiction of instability, well, explained the stability of atom, but he also explained the spectral light, the spectrum of hydrogen atoms. Well, for hydrogen, Niels Bohr theory, so combination of Planck's constant and his own postulates was sort of gave some light, and it corresponded to what experiment showed to us, because these spectra of hydrogen were found experimentally. So already at that time we knew the spectrum lights, or it's called linear spectrum. Linear spectrum. No, linear. You know what is linear spectrum? Maybe do we have still Maria? I will find Maria. Are you still listening to us, or you lost the thread? Maria Zachinoka.
Yes, I'm here.
So what is linear spectrum?
Sorry,
Yes,
yes.
linear spectrum. Do you understand this linear
Yes,
spectrum?
it's like the discrete spectrum of lines you get when you, for
Yes,
example, study excited states of different atoms. They don't emit
yes.
like it's in a big bunch, but they just emit some
So what I
discrete
want to,
points.
yes, Maria, thank you. What I want to stress is that this linear character of spectrum was known before the revolution in physics. But this linear character of spectrum of hydrogen was not explained. So it remained just an experimental fact, and nobody knew why it is so, why the lines are what they are, okay? Before Niels Bohr proposed his model of atom of hydrogen by using this Planck constant. And when he proposed his solution, so we could understand the mystery of this linear spectrum of hydrogen atom. So what seemed mysterious now was sort of explained, okay, by means of quantum mechanics, so by means of Planck constant. So that is we say the breakthrough or the revolution and the beginning of quantum mechanics. So it is associated with Niels Bohr. Okay, am I speaking correctly, or you have some reservations?
No, we don't have any reservations. You can continue.
Okay, so because this is important, this because you see, if we take the line of thought again, it started from radioactivity. Then radioactivity gave possibility for Rutherford to have a source of alpha particles. Then he used these alpha particles and uh, sort of and like made them run through these foils of gold. Then was created the planetary model of atoms. This planetary model seemed to be unstable because, according to classical electrodynamics, accelerated electrons should emit light. So what did Niels Bohr do? He took the Planck constant, which was proposed by Planck for quite another task of explaining black body radiation, and used it to explain the motion of electrons in hydrogen atoms. So now motion was regarded not as a continuous process with velocity being a derivative of, say, displacement by time, okay? But now it was considered as a change like leaps. So sort of electron was moving by leaps. So either he was on a stable orbit, so he sort of didn't move or moved in such a way as not to emit energy, or he changed the orbit, and while changing the orbit he emitted a quantum of light, which was the like the division of this sort of um, how to say, change of energy between these two levels, and this change of, or how to say, not change of energy but difference of energies. Yes, so if one level had energy
Query.
E1, huh?
I have a
How you can,
query. Yeah, this is about 20th century, right? We have completed 19th century.
yes, this was proposed by Niels Bohr in 1913. So you see, so if we just take the dates, mm, H nu, okay. So you see, so H nu is equal to the difference of energy levels, okay? So if electron comes from energy level E1 to energy level E2, it emits or also he can not emit, but what is the opposition of emission? It can поглотить or no,
Absorb.
Absorption,
yes.
absorption.
So yes, emission or absorption. So it depends. If an electron comes from one level to another, it can absorb a light quanta from without, and then he can the atom which absorbed this quantum of light will come into a energetically more higher state. Okay, so it is called also well, in Russian it's возбужденный. I maybe in English it's like this, not disturbed, but
Excited.
excited state. Yes. So yes.
Excited state.
So now we see the hydrogen atom as a set of different kinds of states. So one is like ground state, and all others are more or less excited states. Okay. So and we can now find not only the uh, uh, there are several sets of spectral lines in hydrogen spectrum. There is a one is a Rydberg, um, I'm sorry, a Rydberg um, series, and another is Lyman, I think, Lyman series. Well, I'm not. I have been studying physics, but now I have a little bit forgotten that. But I know that there are several series. So Rydberg series seems to start from ground state to all excited states. Well, just one by one. And Lyman series starts from the first excited states to the second, the third, and so on. So you see that there will be different, like, well, different quantities you will receive by. So this is well, there are also another series. So there can be even more series of spectral lines. So all of them were more or less like explained by Niels Bohr theory. So the dates are, now we can, if we want the dates, so the first date is 1896. This is the discovery of radioactivity. The second date is 1911. This is the experiments of Rutherford with golden foils and alpha particles. Then the third date is 1913. This is the solution proposed by Niels Bohr, the model of hydrogen atom proposed by Niels Bohr. And the fourth date is 1900. It's the discovery of the quantum of action and the discovery, reintroducing of corpuscular theory of light. Okay, so all in all, these four events led to revolution in our concept of motion, in our concept of light, in our concept of radiation, in our concept of chemical elements. So everything has changed. So that's led Max Planck, who was, who introduced this Planck constant. This led Max Planck to formulate his so-called Berlin speech. Also, it was the ideas of this speech were later formulated by him in his Nobel speech. Well, when he received the Nobel Prize in Physics, Max Planck. So Max Planck in both those speeches one of the speeches was pronounced in 1913 between among to the students of the Berlin University. Another speech was made by him while receiving the Nobel Prize. I think it was in 1920. Well, I'm not sure about the exact date when Max Planck received the Nobel Prize, but here when a physicist or any other man receives Nobel Prize, say for literature, or Nobel Peace Prize or Nobel Prize in physics, he can deliver a so-called Nobel speech. You understand? Anshita, I think it's easy. Nobel speech. Maybe Marie Curie also delivered Nobel speech. Yes? Uh, Rilon, it's okay with Nobel speech.
Yes,
Nobel
yes, Prof.
speech. When you receive a Nobel Prize, you are given an opportunity to say something to the world. And you can use this opportunity. So Max Planck used this opportunity to speak about scientific revolution. So revolutionary changes which happened in physics at the threshold, threshold. Yes, am I pronouncing hold? Well, this like that, threshold, threshold. Yes, like that, threshold. Is it okay? Mehdi, threshold. That's like a step between two centuries, okay? Like the door. Yes, it's this word is not good for you. Threshold. Who knows this word? Or maybe I'm writing it not correctly. I will see.
Can you explain it to us, please?
Yes, I will do it.
Well, I think
Threshold.
it's written correctly.
Yes, I will just give you an example in Cambridge Dictionary.
Threshold.
Threshold, the floor of an entrance to a building or room. Okay. I'm sorry.
I am asking about Nobel speech, not threshold.
Well, I will uh, just copy it from Cambridge Dictionary and um, I will insert it into our chat. So the floor of an entrance to a building or room. So if you pass if you go into a into a building or into a room, you have to pass through a threshold. So there is a threshold between two centuries, 19th century and 20th century. So on the threshold between these two centuries happened scientific revolution, okay? So it started in the end of the 19th century and ended already in the 20th century. And important event took place exactly in 1900. So what we can say threshold, okay? So 2 centuries, you see, 19th and 20th. That's why I'm using this word, threshold. So what happened? So um, uh, we passed to another set of realities. So we had to change our ideas. What is motion? For example, we had very beautiful idea of a trajectory. Yes, or that the velocity is the derivative of displacement by time. So now we have to leave those ideas. They are like outdated. Now nobody speaks about trajectory. Only we say it's an approximation. But if we take the motion of electron in a nucleus, moving around the nucleus, we cannot say that electron is moving on a certain trajectory or certain orbit like the planet around the sun. Okay, this is not so. Uh, the motion of electron in the atom cannot be explained in classical like ideas such as trajectory or derivative or momentary velocity or something like that. We have to invent quite new explanation of what is motion. So now motion is a change between two states. So there's a certain idea of quantum states. Quantum states. You understand quantum states? Is it difficult for you or not, Anshita? Quantum states. Have you studied quantum mechanics or
No,
not?
because this is not my field, and I'm not
I
being
see.
even. I don't.
Yes. So, but you don't need just particular formulas or only the idea. What is quantum state? So this just look in the dictionary. What is quantum state?
Okay.
Maybe somebody studied. Maybe I don't know. I think part, Maria Zaychinoka. Are you still with us, Maria?
I studied physics.
She is not with us. But Angel Sierra, are you with us?
Yeah.
I'm
So,
here.
uh,
I just have some mic problems.
okay.
Yes.
So, do you know what is quantum states?
Quantum
Quantum
states.
states. Yes,
Yes.
you
It's
know.
like the full description of the quantum system, I'd say.
Yes,
And
yes, exactly.
this system may be in different states, but
Yes,
at the right moment, it has like the ability to be in the specific one.
yes. Now, what is ground state? Ground
Uh,
state.
it's like not the excited one.
Yes,
I'd
not the
say
excited one. So,
it's like with the minimal energy.
yes, okay, that's it exactly. So now you can imagine that in the 19th century, there was no talk about quantum states, ground state, excited state. This all appeared after Niels Bohr proposed his first variant of quantum mechanics, okay? Agreed? So before Niels Bohr, nobody spoke about those quantum states. They were not known. And when something appears which was previously just not known at all, and even these words were not used before 1913, so we can speak about the revolution. That was the idea of Max Planck's Nobel speech and Max Planck's speech before the students of Berlin University in 1913. So you can use these both speeches. I will give you links. We have, I think, Anshita, we have also Vkontakte, we have a group devoted to philosophy of science. And we have also the group in WhatsApp. So I promise you to give links to these two speeches of Max Planck, from which you can gain the idea what is the scientific revolution of the 20th century, okay, of the beginning of the 20th century. So this will be your home task to study these speeches. They are not difficult because the Nobel speech is given to all the world. So Max Planck did it somehow understanding that not all people are physicists, okay? This is good, d'accord? So I can say goodbye for you, yes? And wish you good night. Yes, so unfortunately I didn't touch all the problems, but